So, chapter 6, probably my favourite chapter in the whole of this book. We're going to be looking at projectiles and projectile motion. Now, projectile motion is what we call motion of something falling through the air. So, for instance, if you were to take a tennis ball and throw it to your friend, I'm sure you can picture the path that it would take through the air. Generally, from the point of throwing, it's going to come up and down and form that kind of path. Now, depending on whether or not you've thrown it from above the ground, the path might carry on down like that, for instance. It all depends on where it's been projected from. But you'll recognise the shape of this motion because this is a parabola, which is the shape of a quadratic equation. And believe it or not, and we'll see throughout this chapter why, projectile motion always forms a parabolic shape. So projectile motion is modelled using quadratic equations. Now, there's a few bits of prerequisite knowledge that you need in order to access the work in this chapter. The first one is I need you to remember what you've learnt about vectors, and specifically, if you have a vector pointing in any direction, you can resolve that vector into horizontal and vertical components. Now, if we call the angle that this vector makes with a horizontal alpha, and if we call the length of this line lowercase u, without the vector line now, because I'm just talking about the magnitude of it rather than the vector itself, then the horizontal component is u cos alpha, and the vertical component is u sine alpha. And that's something you've done a lot of already, and you will do a lot more of throughout this chapter. You also need to know your kinematics equations, sometimes called the SUVAT or the UVAST equations. So let's remind ourselves what they are. We've got things like V equals U plus AT. We've got S equals half U plus VT, which you may instead have seen written something like this. You've also got v squared is u squared plus 2as, and then you've got everybody's favourite, s equals ut plus half at squared, and then everybody's least favourite, the variant on that one, which is vt minus half at squared. Now, the other thing you need to remember is when you've looked at things like particles being projected vertically upwards, you've thought about the idea of acceleration due to gravity. And you know that acceleration due to gravity is g, which is approximately 9.8 metres per second squared. Now, please be aware that in your mathematics exams, unless you're told otherwise, which generally you're not, you take G to be 9.8. I know some of you do your A-level in physics, and I think you use G as 9.81 in physics, but in maths we stick to 9.8. And it's worth pointing out that because this is rounded to two significant figures, then the minute you use this number, the most accurate your answer will ever be is two significant figures. Now, the examiners allow you a little bit of leeway, so they will let you give an answer to three significant figures, but if you give any more accuracy, it's just wrong. So all answers, we're going to stick with 3SF because then it's just consistent. Always do 3SF and then you know you're going to be okay. So we're going to look at horizontal projection first of all. Horizontal projection is where, imagine you're kind of standing on a cliff and you throw something horizontally off the top of the cliff, like a rock into the sea, and its motion goes down like that, and the rock lands and splashes in the sea. That's horizontal projection. And on horizontal projection, your angle of projection here, imagine bringing this vector, let me show you with my pen, bringing this vector down to the horizontal, that angle is 0. So for horizontal projection, we use alpha is 0, and it's worth pointing out at this point that cos of 0 is 1, but sine of 0 is 0. So when we're looking at horizontal and vertical components, there's no vertical component here. I mean, you can see that, can't you? This vector points horizontally across, but I'm just going to point it out for you. So let's have a look at the first example. Example 1 tells us that a particle is projected horizontally at 25 metres per second from 78.4 metres above a horizontal surface. And we've got a couple of things to find. The first thing you're going to do in every single question, just like you do always in mechanics, is draw a diagram. Do not do these questions without a diagram. If you try and do that, then you're some word that I probably shouldn't say because I'm a teacher. Do not do these, you know what I mean. Don't do these questions without a diagram. So what we've got is a point 78.4 metres up. And from that point, a particle is projected horizontally at 25 metres per second. And you know that it's going to go like that until it hits the ground. Now, we don't know how far along it hits the ground, so we will call that distance x. Now, if that distance is x, then first of all, we have got to work out the time taken to reach the ground. We're going to take the same approach to every single projectiles question from the beginning all the way through to the end of this chapter. So the first thing we're going to do is we're going to list for this situation suvat, but in vector form. So you're going to do column vectors like this. And we know, first of all, that our displacement from where we started horizontally is x, and vertically it's gone down by 78.4. So we represent that as minus 78.4. So just to point out at this stage that we take horizontal to be positive, horizontal to the right, sorry, to be positive, and we take vertical upwards to be positive. So anything going down will be negative. So we've got x horizontally and minus 78.4 vertically. Now, u is our initial velocity. So the horizontal component of that is 25 cos 0, because our angle of projection is 0. And our vertical one is 25 sine 0. But let's work these out. We already mentioned before that cos 0 is 1, so that's 25, and sine 0 is 0. So that is our projection. Now our final velocity when we hit the ground, don't know that. Don't know if I'm interested in it, probably not for this question. We'll think about that in a second. Now our acceleration due to gravity. Let's point this out really, really clearly. Acceleration due to gravity always comes down vertically towards the ground. So it will always, in every question, look like this. No horizontal component at all, but a vertical component of minus g. So acceleration due to gravity down, g coming down, so we represent it as minus g. Now, finally, the time of travel, that's what we've actually got to work out here. So that's t. Now, notice that all four of these first ones are vectors. Time is not a vector. It has no horizontal and vertical components. It's just time. So just like we did with kinematics, we look at these four quantities and we say, the ones we're interested in, sorry, so S, U, A and T, because we've got to work out T. And say which equation links them. S, U, A and T, it's everybody's favourite. S equals ut plus half at squared. But where we have vectors, write them with your vector lines and then put in your vector component with both components. So x and minus 78.4. And then for u, we've got 25 and 0. And then plus half a, 0 and minus g, and t squared. Now, the reason we do that is because tied up in this, we have two separate equations. We have our horizontal equation and our vertical equation. So let's take our horizontal equation and write it out. That gives me x equals 25t plus half lots of 0 times t squared, so it's just 0. So that's just that. Now let's take our vertical equation and write it out. We've got minus 78.4 equals, we're going on the bottom line here, 0, so I don't need to write anything there, plus half lots of minus gt squared. So that's minus half gt squared. Now, in order to answer part A, find the time travelled, I can't use this one because I don't know x, but I can use this one because the only unknown here is t, because of course g I use as 9.8. So let's work with that one. And we have got minus 78.4 divided by minus a half. That's this value here. I'm also now going to divide it by g, so by 9.8. And that gives me t squared is 16, which means that t, obviously if I square it 16, I've got plus or minus 4, but minus 4 seconds doesn't make sense. So I'm going to take 4 seconds there. Now, I've done the hard work to answer part B here, because part B wants me to find the horizontal distance travelled, and the horizontal distance travelled is x. I've already got the equation for it. X is 25t. So let's copy that out. T was 4 seconds. So x is 100 metres. Let's have a look at example 2. This time we have something that's being projected horizontally, a particle projected horizontally with a velocity of 15 metres per second. I'm going to do a little diagram again. Didn't leave myself much space for this, but that was silly. Do you know what? I'm not going to need this much space to answer part B, so I'm just going to do my diagram here for now. My apologies. So it is projected horizontally with a speed of 15. We've got to find the horizontal and vertical components of the displacement after 3 seconds. So what happens is, imagine you're up on a cliff. This goes horizontally like that. And after 3 seconds, like this point here, it wants to know the horizontal and the vertical components of the displacement. So let's mark them on, shall we? It's moved this much horizontally, this much vertically, so we've got x and y there. So let's set up some equations. We're going to start off by writing out, just like before, SUVAT, because we're going to do every question in the same way. So after 3 seconds, we're talking about our horizontal displacement is x and our vertical displacement is minus y, because we've gone down by a distance of y. U was 15 cos 0, because our angle of projection is 0, 15 sine 0. But cos 0 is 1, so that's just 15, sine 0 is 0. V doesn't ask me to find that, not even mentioning that, so we'll leave that for now. V in this context would be the speed we're travelling at when we, or the velocity we're travelling at, sorry, when we hit this point here, but I'm not interested in it, so we'll leave that. A is always 0 minus g, because it's coming down, and up is positive, and T is 3 because it's after 3 seconds. So we've got to find x and y, so we're using S, U, A and T again. So let's write out our equation. S equals ut plus half at squared, and note that I've indicated which of these are vectors. Plug in the vectors that we have. I almost wrote t then instead of 3. There we go. Now let's do our horizontal equation. X is 15 times 3 is 45, plus 0 times half times 3 squared is just 0. So we found the horizontal component. And the vertical one, minus y, is 0 times 3, so 0. Do you know what? Let's write it out in full. There we go. So we'll put the 0 here as well. And then we've got minus half g times 3 squared. So that gives me minus y is minus half times g times 3 squared is 44.1. So y is 44.1 metres. So I know after 3 seconds I've travelled horizontally by 45 metres, and then vertically but down by 44.1 metres. Now, in part B, it asks me to find the distance from the starting point after 3 seconds. Now, let's mark that in a different colour on here, and we'll work it out in a different colour so you can see what's going on. We had x as 45 and y as 44.1 down. But the distance from where you started to where you are after 3 seconds is that. That's the distance in question. Now you have a right angled triangle here, so we can apply Pythagoras' theorem. So let's call this distance d, and d is going to be the square root of 45 squared plus 44.1 squared. And that comes out as 63.0 metres to 3 significant figures. And we said we're going to give all our answers to 3 significant figures. There we go. Let's have a look at example 3. So a particle is projected horizontally again. Horizontally tells us that our angle of projection is 0. And we are going this time at a speed of u, so we don't know this, but we do know that we're 122.5 metres above the ground. And we also know that we hit the ground horizontally a distance of 90 metres from where we started. And we've got to find this speed that we were projected with. Again, we'll draw a diagram. Got to draw a diagram. So we are projected horizontally with the speed of u. It's going to be something like this. Now this is not to scale at all because this is a distance of 122.5 and this is a distance of 90. Obviously it's not to scale, but it's a diagram. That's all I need it for, just to picture what's going on. So just like we did before, we write out our suvat. Our displacement from where we started, remember that up is positive, right is positive, so we've gone right by 90, but we've gone down by 122.5, so that's minus 122.5 there. U is capital U cos 0, because it's always U cos alpha, alpha is 0, and then U sine alpha, so alpha is 0. Tidy that up, cos 0 is 1, sine 0 is 0. You'll notice for all the questions we've done so far that our initial velocity always ends up being something 0. That's only because we're projecting horizontally. In a moment, in some of the later videos, we're not going to project horizontally, so I'm emphasising the point of what we always do. It's just in this case, our angles are 0. We're not interested in V, don't need to know what speed I'm going at when I hit the ground. We are interested in A because we know it anyway, so that's 0 minus G. And the time doesn't tell us. U 122 or 90, yeah, it doesn't tell us. So let's have a think about this. We have got S, U, A. We need 4 of these to use an equation, so I'm going to have to use T, even though I don't know it, so I'm going to have to work it out probably before I can do anything else. So let's have a look at what happens. Everyone's favourite again? You'll find that there's a recurring theme here in that we use this equation particularly a lot. So plug in what we know. Write out our horizontal equation. We've got a plus 0 there, so that's just 90 equals ut. Write out our vertical equation. We've got 0t, so I'll just leave that blank, minus half gt squared. Now, look at this one. I can solve this one because I've only got one unknown, that's t. So let's solve that one. So we've got minus 122.5, divide it by minus a half, and divide it by g to get t squared is 25. And of course that tells us that t is 5 seconds, because -5 is not useful to this question. It does have a kind of context, I'll talk about that in a moment, but 5 seconds, there we go. Now, oh, my computer's being noisy, excuse me. Then we've got the value of t is 5, and we're now going to plug that into the other equation, the horizontal one, to work out the value of u. So 90 equals u times 5, which means that u would be 90 over 5, which is of course 18 metres per second. And that was what we had to find. Now, very briefly, before you start exercise 6a, I just wanted to point out that although it doesn't actually have a particular meaning, the -5 as the other square root of 25, in terms of the quadratic, what it means is we're in the middle of the motion here. We've got 5 seconds going that way. If I were to go back the other way, or going like off the screen, in fact, let's move it. If I were to go back the other way here, and back to 0, then that section of the journey would have been 5 seconds, and then this section is another 5 seconds. But of course we started here, so we'll always start from t is 0. So have a go at exercise 3a, and then we'll go on to some more interesting examples in a bit where the angle of projection is not horizontal, but maybe we're kind of throwing it up in the air and coming down.